by Emmanuel Rauzy, who will tell us about groups with EDT0L presentations.
All right, thank you, Laurent, and thank you all for being here. Today, I want to discuss groups with presentation in EDT0L. Let's start by some basic definition about presentation. A finite set will be called an alphabet. A star, the team star, is a set of words correctly. The subset of a star is a language. And finally, a class of languages which are denoted always with several capital letters, denote classes of languages. Well, you could say that it's a map which maps a finite set to an element which is the set of languages over this finite set. So class of languages, something that maps an alphabet to a set of languages over this. Now, let us talk about group presentation. For that, I need the definition of a marked group. A marked group is just a group with a generating interval. This set S is an order set. The order matters, and the identity element could be in it, but it has to generate the whole group. And this definition is not interesting unless we have the definition of a morphism of marked groups. Marked group GS to a marked group H. That's right. It's just a group homomorphism which maps the first double to the second double. So a group homomorphism type is that phi from S phi to S prime. So there's at most one morphism of marked groups from a marked group to another marked group, and they are isomorphic as marked group exactly when they are morphism in both directions. So finally, the marked group has a presentation in the class of languages, and if there is a language over the generator and their inverses, such that the marked group is the quotient of a group by the normal total of the language. Generated by the generators.
Sorry, there's a question or remark?
זהו.
אתה שומע? מהקטן?
אני שומע, עכשיו אני חיברתי את זה פה. זה עובד, אני חושב.
טוב, אין לי מושג.
What is it?
I think Aries micro is activated by mistake. Can you settle it?
So I can keep going. Notation, time of a certain class of languages is the set of groups with the presentation in this type of method. This is the setting. As an introductory example, maybe I'll discuss recursive presentation, because this notion of a group that has a presentation in a certain class of languages, it's often used with finite presentation and with recursive presentation, and much of the other classes of languages are left out. And so I'll first discuss this class of group with recursive presentation. So, right, is the languages recognized by Turing. There's a Turing machine that computes the characteristic language of the characteristic functions of the language. Now, if you look at articles which talk about recursive presentation, an example of a recursively presented group which you'll often find is, for instance, the length item. This is a recursively presented group, and for presentation, you can write down, for instance, it would be one generator and folder 2, and when we conjugate this generator by power of the second generator, it commutes with the third generator. It's very easy to write a Turing machine that recognizes this language, so it's a recursive presentation. Now, if I ask you the following question, from this presentation, can you find the abelianized of the length item? Yes, it's very easy. You say that those two generators should commute, and you see that all these relations disappear as soon as A and T commute. Then you're left with a presentation. So the abelianized is just two direct products, and it's a trivial thing to compute. But now, let me give you a few propositions on what we can do from recursive presentation. We take two marked groups which are recursively presented. And we suppose that one is a strict quotient of the other. One is a strict quotient of the other. Then, in this case, no algorithm can, on input if S or H S prime given by a recursive presentation, decide which is. This is something silly, but the isomorphism problem, even for two marked groups, is unsolvable when groups are given by recursive presentation. And as a corollary, this proposition, an easy corollary, you see that if P is a semi-decidable property, so a property that we can prove when a group has it. Well, for recursive presentation, then P is quotient stable. And as a second corollary to the fact that the semi-decidable property is quotient stable, we get that we cannot compute the abelianized of a group given a recursive presentation of this group. So semi-decidable means there's an algorithm which will stop exactly when the group has the set property. So completely decidable. And something is decidable exactly when it is semi-decidable and it's complement. It's also semi-decidable.
So about the proposition, there's no algorithm that can on input a group isomorphic to, or what exactly do you mean?
Recursive presentation,
Yes.
which gives either this or that.
Yeah, but the input is a presentation. It's not this or that. If there's only two inputs,
Is the input guaranteed to be one or the other?
Yes,
Okay.
exactly. Yes.
Exactly.
You are given a recursive presentation. So being given a recursive presentation means being given the code for a Turing machine that recognizes the relators of your presentation.
so more formally it's given a K, comma, S double prime, and a guarantee that this is isomorphic to GS or HS prime as a marked group.
And this is a bit silly, or this is very easy, but you have an algorithm that recognizes relations, and if you see only relations that belong to the bigger group, you can never conclude that it's the bigger group, because at any point a relation that is only satisfied by this one could appear, and in fact it will be this one. Yes.
What does mean that algorithm recognizes relation? It means that the set of relations is decidable or recursively in an array.
So in this case, it's actually equivalent, meaning if you have a presentation where the set of relations is recursively enumerable, you can find another presentation where for the same marked group, but with a recursive presentation. And in fact, in the literature, it's often used interchangeably, whether you have a recursively enumerable presentation or a recursive presentation, but it's completely equivalent, even in the algorithm.
It's kind
But
of
here I say
wait, it's kind of strange. So you're saying that the enumerable representation is the same as decidable.
yes, yes.
Yes.
But recognizing the words, not recognizing the words in the presentation, not recognizing the word problem. This is a standard trick. You give yourself as relators all the words plus identity to the power, the number of times you need to recognize it. You give yourself a free extra generator, which is identity.
Then you would know when to stop the algorithm. Like you have extra information in the presentation that tells you.
You can just pollute your
Okay,
words
so it's
by enough.
okay, so because it's subset, not the whole set of
Exactly.
Yeah. Yeah.
Right. So this is not very complicated, but why I think this is interesting is because more often than not, and not only in the case of the long type of groups, but presentations which are said to be recursive are then used, but in fact we use the fact that they have much better properties. This is much better than just a recursive presentation, and the presentation of a recursive group is much better than a recursive presentation, and this points out to some lack of vocabulary, if you want, that we should be able to say, why is this better than just a recursive presentation? Because it is a EDT0L presentation. Still, there are some semi-decidable properties of recursively presented group. For instance, having polynomial group. By a famous theorem of Roma. Or having Cashman property T. By work of Ozawa. Or being finite. Just as a consequence of the true or false. But this shows that some things are non-trivial, even if you don't know the decidability of now, we want to find new examples of classes of languages which are relevant to study group presentations. And that's where we introduce the L family. Named after Lyndon Mayer. It's not one class of languages, it's a whole class of languages, and I will give you some of them. I can't give them all because there are many, many of them. So I picked an alphabet A. The EDT0L system. The EDT0L system is a word over A plus 5, which is a finite set of endomorphisms of monoid morphisms from A star to A star. The EDT0L system is a finite set of words together with the same set of with the same finite set of endomorphisms. Now we need also EDT0L system.
I don't understand. So how? So you said you define a language, but you define set
For now, I define just the system.
the system.
That's the book of the
Okay.
So this defines a language, which will be the union of the iteration, and you'll get a language.
So what is the starting point?
W0, a word.
The
Okay.
system
So
is
you
a
have
word and a finite set of endomorphisms.
okay.
And then when you have a finite set of endomorphisms, you can write and a finite set of words. This is the set of W, 5, and big 5. W. This gives you a set of words. And also you can write 5 to the end of the composition. When you have such a system, you can define language like that. And when you have a GTF0 system, you just start with finitely many words, and you have the same formula but starting with the finitely many words. And an EDT0L system is a GTF0L system. Over A union N, the new alphabet. You add a new alphabet of letters which are called non-terminals, and you take a GTF0L system. No, sorry, a GT0L system. And the language it gives you, well, you have this system which, as above, defines this language. But this language is a language over all these letters, and we don't want that to just intersect with A star.
So then what is so what is so is it precisely the context-free languages or not?
No. So
No, of course, yeah, sure.
So the difference with context-free
Sure,
and
because
the simultaneous rewriting is called the
it's stronger,
You apply these models
sure,
everywhere, so you would replace all occurrences.
I think it's really
I didn't know.
I think it's really orthogonal.
Yeah.
Not that one is stronger than the other.
It's not system. This is just a EDT0L system over a new language. only over the non-terminals, plus F, which is a monoid morphism from n star to S star. So this is another way of introducing non-terminals. Here we take an intersection, and here we take the image by an endomorphism. And a finite example, not an example, I denote EDT0L plus thing. This is just the class of languages consisting of the EDT0L language union with this is our lot of definition. Example, for instance, the language involved in the presentation of the Lamplighter group, or for instance, T minus n a T n times a. We want to show that all these words form EDT0L language. We can use a new letter A, and we can start with the word W0, which is big A followed by small a. And we use two endomorphisms. Phi 1 turns big A into phi T inverse big A T. And it's the identity on all other letters. And phi 2 will turn big A into small a. And it's the identity on all other letters. And you see that when you start with this word, then you apply these two morphisms to set up, you will get exactly this language. So, health system, these type of languages were introduced by Lyndon Meyer to study biology, but much of the work was done by Rosenberg and Salomar. In the 70s, let's say. EDT0L is a proper class of EDT0L, which is a proper class of EDT0L plus 3, which is a proper class of EDT0L. This is going down, which is the same as EDT0L. And this is a proper subclass of recursive languages. Proof is the theorem is much bigger, and there are many more languages because it's an exponential of the number of letters. So we have many languages. These theorems what's interesting also is the method of proof to these theorems. Those classes of languages are studied, and in the end you get such theorem, but while proving it, you know much more about the languages. Another theorem, more recent. And Elder, 2016 or 2021 for three groups and for hyperbole. Solution set. Equation and three equations in hyperbolic group. Are EDT0L in a space in EDT0L in NP space. What this means is you take a finite set of equations equation and inequation in a hyperbolic group, you can express the set of solutions as a EDT0L language, modulo choosing a certain type of normal form for this world. And in empty space, this means that given the equation, you can find a description of the system, of the EDT0L system, in empty space in time complexity. All right, so this was first true for free groups and then for hyperbolic groups, and actually the precise time complexity is different if you have a torsion-free hyperbolic group or general hyperbolic groups.
What do you mean precise? So it's like, it's actually the result.
The result is a bit more precise.
Uh-huh.
If you could make distinctions, we could say it's non-deterministic or quadratic or dimensional. This is the theorem which revealed EDT0L to the group theory. And ever since, there are many results that show that this class of languages is indeed very useful to have in mind when working in group theory. And ever since, there are many results about you can have a word problem in EDT0L, so solution set in for something completely different, a definition of the wrong. And with its support, a group has an L presentation. If so, we take a finite generating set. If it can be written as a quotient of the free group, like this, R1 given you take two finite sets of relations in the free group. So maybe I can say this is a finite calculation. And phi is the finite set of n1. Then you get this result. And ever since, so the first, this was
And could please R1, U.
I'm sorry.
When is a backslash cup, the other is backslash big cup.
Yes. So the first theorem of Laurent was that self-similar regular contracting rank groups all have such presentations and never have finite presentation. This was a generalization of the result of Lisjonok for the people. And L maybe stands a bit for Lindenmayer and maybe a bit for Lisjonok as well. That's what we told me. And in fact, ever since this definition appeared, in different places, it has turned out to be useful. But now we take a look at this definition, and we want to use formal languages to attach this definition to the global theory of formal language. And what do we see? That this is exactly this is proof this presentation in EDT0L, but and the starting idea of this project is that EDT0L in terms of language theory, it's not a very good class of languages because it has bad closure properties. It is not stable by taking homomorphism, by concatenations, intersection with regular languages. This type of stability results are those that are looked for. And in the work of Rosenberg and Salomar, for instance, they defined 50 classes of languages, and they say, oh, these ones are the ones that have good closure properties, these ones are the ones we'll keep, and the other ones, we'll more or less forget about them. So the first result, quite surprisingly, we want to present today, with Laurent and Léon, is the following. 5 EDT0L is actually the same thing as EDT0L. Those classes of languages are different, but the set of groups that have representation in these classes are identical. Now, we have a nice family of languages and we have presentations, but we'd like to compute quotients. What was not possible for recursive presentations, we'd like to show that it's possible for these EDT0L presentation because shows that we have a nice notion of presentation, so you can compute quotients because presentations of group encode quotients, right? So, including and the same is the following. We will compute a kappa, which is a subgroup function. So kappa of G is a subgroup of G. The term subgroup function is used in the theory of finite group. It just means that it's well defined, that you are defining something which depends only on the isomorphism class of your group when associating with a subgroup. And it should also be true that for any G and H and morphism between G and H, kappa phi of kappa of G is a subgroup of kappa of G. So kappa of G is always a fully characteristic subgroup of your group, but this is even more. This is all these groups together define fully characteristic subgroups. And the last condition, which is going to be that kappa of G is not kappa of D, is a trivial subgroup. For instance, you take the center of a group, it's a well-defined subgroup, but it's not a fully characteristic subgroup, this condition. Now, another example is you take the group generated by torsion element. In any group, you can consider the subgroup generated by element of finite order. And this is well defined and it satisfies this property. But it doesn't satisfy this second property. Now I should give you examples that satisfy all three properties. I'll give you several examples. We'll use such subgroup functors to compute quotients, and we'll use different ones to compute different quotients. We have a functor associated to metadata, which is just a second derived subgroup. And we will also compute nilpotent quotients. And here we'll consider the lower central series, so gamma 1 for G is P, and gamma K plus 1 is gamma K integral G. And finite quotients also we will compute, and free quotients. And in each case, we take associated to a finite group F. We can take all morphisms on G to the finite group F. We take the intersection of the terms, and that gives us a nice subgroup. And for free group, we take the same thing. For all morphism from the group B to a free group, we can take the intersection. So this is the whole family. This is one subgroup functor for each K, and this is one for each time. And it's easy to see that they satisfy the condition over there. All right, a notation which will be G mod kappa of G will be G mod. And now consider a group mod group given by the EDT0L representation. So we take a group G, and it's given to us as the S with relation F of a union. With a non-terminal alphabet A, W0 belongs to A star, and F is an endomorphism from A star to S star. What do we do with that? The first lemma that if the group given by the elimination over non-terminal, where you iterate and you take the quotient by this subgroup contour, if this stabilizes, meaning this is the same as taking from N to a certain P, if this stabilizes like that, then the same holds when you take the image by X. So then these are just the properties of this subgroup control that applying it several times in a row to stabilize it and so on. The no difficulty. And the second lemma is that for the kappa in the table, as I introduced before, star will occur. And it can be detected. Algorithmically speaking. Let me just say a word on the proof of this second lemma. There are two cases for when you consider Metabolian, the functions associated to Metabolian groups or nilpotent groups or finite groups, you get that when you quotient even the free group by this subgroup function, you have a group with the max n property. The max n property is the increasing sequences of normal subgroup stabilized. Every normal subgroup is finitely generated as a normal subgroup. So the max n property, which is it's a theorem of all that Methodological groups have the map and property. And I think we also did it for the important groups, which have actual materiality. So this property will imply that equality will occur. And then to detect it, detection is by the world problem. You just have to check that when we add finitely many new relations, we haven't changed anything, and this will be solved by using the world problem on finitely many elements. But for free groups, it's actually different, because when we quantify this subgroup functor here, we have a residually free group. We take the residually free image, and the residually free groups don't satisfy max n because free groups are residually free. We have a different argument for stabilization. It's equational materiality. Which is the fact that every infinite system of equations over a free group is equivalent to a finite subsystem of it. It's a theorem of Hubbard for free group. I wrote the thing. And this guarantees that equality will occur at some point, but then we have to detect it. And detecting it is again solving the world problem, but solving the world problem in groups given as residually free groups. And the detection is actually then solved by detected by using the universal theory of free groups. Which is what a theorem of Maccabi that is solvable. To know if for some p and some n here you have the same group, you have to ask, are those finitely many relations, are those finitely many relations here equivalent to those finitely many relations in all free groups? You ask, are these relations equivalent to these relations in all free groups? And this is a universal sentence in the theory of free groups. And by mechanics theorem, it's always possible to decide whether or not this is the case. It's the simultaneous word problem on all free groups. And in fact, equational materiality and solvability of the universal theory has been extended to shortened free hyperbolic groups and even shortened and even all hyperbolic groups. So this could be extended to all hyperbolic. All right, so the theorem, which extends and unifies Laurent with Bettina Beck and René Martoun in 2008 and 2011. They had the case Newton groups in 2008 and finite group in 2011. So the result is that there is an algorithm that takes as input a marked group given by an EDT0L presentation, or given by the EDT0L system, and a marked group given by a finite presentation. And which is either free Machiavellian finite omnipotent, and the output is just we have a quotient. Output does the S map So actually, it's not true that there is an algorithm. There are. You have one for each case. It's not uniform or. And the proof of that, once we have or through them, is very simple. The proof is that in each case, this equality, there is a morphism here. If and only if we have one after quotienting by the subgroup pointer. Well, if you have chosen the right subgroup pointer, but you can choose one in each case so that this will occur. And then when this is given by a relative finite presentation, meaning this is given by a finitely presented group quotiented by kappa. This is a representation, finite presentation modulo kappa, and asking is this a marked quotient is equivalent to the work problem again. If you see this, the finite presentation modulo kappa reduces it to this to the work problem. All right. Now the last remark I want to make, which is the following: phi red is not equal to phi. So above we have seen that we have a computable map which takes as input which tells us if we have a point. And we've seen that it's computable whenever this first group is given by EDT0L presentation, and the second group is given by a finite presentation, and it should be either Mendelian or important, or this is a uniform result. And we can actually say something less. We can take this result and weaken it a little bit and say that for all group which is EDT0L, the map of the second variable we fix the first variable and we let the second variable, and this should be computable. And this is a weaker result, but why is it interesting? It's interesting because now this is a property of the group G that this map is computable. This defines a property. And is this an interesting property? Well, in fact, in the case of H being a free group or H being a metabolism group, it's a trivial property. Every group satisfies it. Every group has computable free quotients, and every group has computable finite quotients. So when we do this restriction for the case of free and metabolism quotients, we get no information at all on our group. But when we do this restriction for nilpotent and finite quotients, we get the last theorem of today. There is a residually the finite or nilpotent group with solvable work problem. Work problem. But non-computable finite or nilpotent portions. So such that the map written here is not computable. And as a consequence of this, we've proved that there are examples of recursively presented groups which do not have EDT0L presentation. And this is actually the only group property we can say for sure. If a group has an EDT0L presentation, it has this property. These are the only examples for now we have of non-trivial properties of EDT0L. All right, thank you for your attention.
Thank you very much. And again, we're ready for questions or remarks. Well, I can start at least. So there is this claim that for finite or free, well, if you fix a finite or a free group, then the maximal quotient with respect to all the kernels of maps to these is computable. But if we replace this by a hyperbolic group, you seem to say that half of it is known to be true. If I fix a hyperbolic group, gamma, S, and I want to determine whether my EDT0L presented group maps onto this hyperbolic group, is this decidable? It would cover the free and the finite case.
I wanted to check with Simon that he had, but I'm pretty sure it works for portion free hyperbolic. So yes, you if gamma is a hyperbolic group, by equational notariality, which holds for all hyperbolic groups in the every residually gamma group is finitely presented as a residually gamma group. So every residually gamma group is a finite presentation modulo this subgroup functor, which is associated to the group gamma, which is just the intersection. And for EDT0L, we can find a finite presentation of the residually gamma image.
Yeah, so if you look at the board, you say equational notariality, GUBA, but then this is also known for hyperbolic groups by Sella, and universal theory, this is also known.
And so the universal theory of
hyperbolic groups.
Each hyperbolic group, yes, it should be done by Damani and Girardel, and it should be uniform in the hyperbolic group. Meaning, given the finite presentation of the hyperbolic group, I can obtain enough reason to solve its universal theory. And I wasn't sure about this. I need to ask Simon about that.
Well, we should ask Vincent.
I could ask Vincent. The universal theory of hyperbolic groups, if you take them both at the same time, it's undecidable. But each one of them has a decidable.
So this is the first example of a group without EDT0L, definitely without EDT0L for that presentation. But could it be that this is like this property is exclusive to EDT0L, or could it be that there's I mean, is there any do you know of any reason to think that to conjecture that this is only the EDT0L presentations that have this?
That's a good question. When you do the proof and the way notariality works, and the EDT0L conditions seem to be really the good conditions to have notariality be effective. So in this case, the problem is always detecting stabilization, because when use recursive presentations. You can always have sequencing of presentation. You know it will stabilize, but you have no way of saying it will, of detecting that it has stabilized. And EDT0L seems to be a very good class of language to allow you to use the abstract fact that things are invariant and to turn into algorithms. But other than the fact that it seems to be I can't tell you anything, and so in between those two classes, I'm not able to give any non-trivial content. I correct contains something non-trivially, which contains EDT0L. I don't know.
It's really interesting.
I think so. Yes, definitely.
No more questions? No more remarks? Well, a big
I-
thank you. Oh,
May
okay.
I
I
ask-
have a question. Yes, please.
A very naive question just about the definition. Maybe I didn't got something. If you have a group which is residually nilpotent, then by definition, nilpotent quotients are computable or what, or not necessarily?
If you have a group which is residually important, it might not have computable nilpotent quotients. We have
So
precisely
then one can ask, because your result, you have an example which is residually finite, where quotients are not computable, and you say maybe one can ask even much more if there is a group with really residually important but not computable quotients, or
these are two results. One result for residually finite, and the same result holds for residually nilpotent. The same holds replacing finite by nilpotent.
So you have an example. So I didn't see very good on the blackboard. So you have examples of residually nilpotent groups, but where nilpotent quotients are not computable. Is it so? Yes.
Residually nilpotent, and given K, there's no algorithm that given K computes a finite presentation of this group modulo gamma K. We use Paul's group, which you probably know.
I didn't follow. You say you use the group of Hall or what?
Quotient, yes, you take Paul's group and you add some relations
But
to it.
which was of Philip Hall, or which solvable groups of Philip Hall, or which one?
The one with infinitely many copies of Z as a center.
Yes, in his construction of solvable groups with prescribed center, yes. And you consider just quotients. So your groups are free-step solvable or what?
Yes, a central quotient of it gives the example.
I haven't understood. Your group in your theorem, are they solvable of step 3? No?
Yes, because it's a central quotient of Paul's free.
Yes, and just for this construction of Philip Hall, you show that they enjoy this property that these nilpotent quotients are not computable for appropriate quotient. Right? Okay.
The idea is very simple. You have to quotient by relations, which when you add a big relation, it doesn't impact the world problem, but it might impact small. So adding a very big relation doesn't change equality between small worlds, but it might appear in nilpotent quotients of small nilpotency degree. You might have arbitrarily big relations, which still have consequences in nilpotent quotients of finite nilpotency class. And using this, we get this result.
Okay, very good. Well, I still would like us to thank all speakers from the day. Simon, Oren, and Emmanuel. And we meet again in 1 month. So that will be on the 13th of December for an afternoon of group theory with more of a dynamical flavor. So we'll be hearing about subshifts of finite type and different questions and topics of interest for group theorists. Hope to see all of you there.